Hi, my name's Andrew McLaren, and I want to help you with center of mass. We're going to look at three different questions from a couple different reference points to show how this formula really works. And I've seen a lot of students get really confused with this because professors they'll show the formula here that like it doesn't really look like your center of mass formula, but the math like it just works out. And students get really confused as to like where these types of like other formulas come from. And I want to help you see how this is just kind of written in a way that it looks different and it's confusing. And really, this should be like a negative number and a positive number that are equal to each other, bringing the center of mass to zero in this problem. So I wouldn't even say that these are two equivalent things. We'll get to that in a little bit, but to get us going, we'll go over the formula visually, three couple questions, and then we'll kind of tie it back to this as well. And we'll have a bonus question. So the formula here is best explained using a visual like this, where you can show the center of mass. You've got two different masses, and this is all relevant to some sort of reference point. So we've got this like reference point, which we're going to mark in green, and all of these things are different distances away. And you can think about the center of mass as like the average of where these masses are. So you've probably done some average problem or even like present composition in chemistry where you've got like different scores and you're trying to figure out like what number is in the middle here based off of the number of things that I have here. So you can think of like mass as like the number, like the amount of tests that you have at that value, and then like the distance as like your score or whatever. And so if you've got like something that's 80 centimeters away and something at 90 centimeters away, but they're equal mass, like they're 1 gram each, then your center of mass is going to be right in the middle. It's going to be 85 centimeters away. So you can think of this as like an average kind of calculation in a sort. If one of these masses is much bigger, like M2, if that's 10 times bigger, then the center of mass is going to get shifted closer. So if it was like 80 and 90, but this is only 1 gram, this is 100 grams, well, your center of mass is going to be almost at 90. It's maybe 88 or 89 away. So that's the general idea and how I think about it in terms of like an average. And you can also change this distance on here and you'll still get the same center of mass. So I could also then like say like, well, I actually want to be much further away. So instead of this being like 80 and 90 away, maybe this is 180, 190, and you should still get the same center of mass. It's you can also see this visually here. A lot of these problems are going to be kind of canceling things out. So there's going to be some sort of masses to the left side and some masses to the right side. But the center of mass is in the center here, so it's 0. So if you have a center of mass that's right in the center here, and you make that your reference point, then you're going to have some negative numbers and positive numbers that are essentially canceling out. So the center of mass ends up being 0. And you can see like in blue, we've got two masses kind of going in the negative direction and our mass going in the positive direction. So there really should be 3 things that we're adding in, not just 2. So this formula is often just shown with like 2 masses, but you can have as many masses as you want in this formula. And here you can see that 2 of them are going to be negative values and 1 will be positive, and those values should cancel out. Okay, so when we have a problem where we're balancing 2 masses, it's really useful to have a diagram and also do a concept check before you do any of the math. So we're going to start by thinking about what this problem kind of looks like. And I'm going to just make a very simple shopping cart. This is our shopping cart that is going to have a length of 0.65 meters from one side to the other. So we've got a little shopping cart looking box or whatever you want to do for that shopping cart. And then within that shopping cart, we have the center of mass that we already know is right here in the middle. And there's some objects relative to that middle. So we've got some cereal box, an apple. So we can make our cereal box something kind of like that. Make our apple something kind of like that looking. And you can, just looking at their masses, figure out which one needs to be further away. So if we look at this, the cereal box looks to be heavier than the apple. So if you were to ask like even a small child, like balance these two objects, a lot of them will be able to tell you the smaller object needs to be further out. And you can kind of just play around with that physically to see that. Now we actually need to do some calculations to get the exact distance on this, but we have a good concept understanding of what we're trying to do, which is a really important start. So we're going to do this problem with a reference point starting here, and everything will be relevant to that reference point at first, and then we're going to do the same thing also looking at from the center and further out. But to start us off, we're just looking at the reference point from here. So the formula that we're using is m1 x1 plus m2 x2, and we only have two objects here, so you don't need to do like m3 and x3. That should be equal to the mass that's total times the center. So this center of mass, the position of the center of mass. So we can think about these as averaging out here in the middle, and there's some value that's blue and some value that's red, kind of representing those two numbers. But what's in the middle here is going to be our center point. So if we think about our masses, let's just go ahead and get our masses labeled on here. Got 0.56 kilograms, and we've got 0.16 kilograms on those two. And we also know the distance of the shopping cart from the center right here. So this distance they've given us 0.06 meters. So we have one piece there, and we know that there's some information. It's like, okay, so what do we know? If I'm looking at this, we have one position, we have one mass. They're asking us to solve for the position with the other mass, but we do know this other mass here. And from that, we should be able to get this information if we have these other two pieces of information. Now, M total isn't directly given, so it's something that you can easily solve for, though, because it's just the masses added up. So if we do that pretty quick, that should be 0.56 plus the 0.16 kilograms. So our mass total here is 0.72 kilograms. So we do have that. And then we also have a displacement of the center of mass here. So that number is also known. So it's not directly given, but it's going to be half of 0.65. So if we've got 0.65, divide that by 2, then that is something that we also know. So 0.325. So now it's just a matter of plugging in everything. This is a method that I use when I'm doing equations, circles and squares. I circle what I have, and I square what I'm looking for. And you should have everything else algebraically to plug in to get that one number. So let's go ahead and actually do that. So we've got our 0.56 kilograms times our, what is that? Well, this is actually the wrong displacement because it's from the center. So we want to use this relative to the side. So we want to do 0.325 minus 0.06. If we want to have this be relevant to our reference point. So we actually are more interested in this number, not this. So I'm going to just change that color real quick just to clarify that. It's just we'll go with purple. So that was given information, which was useful, just not really from the reference point that we want to use. So if we really want to get this number, we're going to need to do that 0.325 minus 0.06. We got 0.265 meters plus some mass here, and that's our mass of the apple. I really like color coding on these problems because there's so many similar things you gotta be keeping track of. X2, which we are solving for, and this will be equal to that total mass, 0.72 kilograms, times the center of mass's displacement. So this is all relevant to this one side. I actually prefer doing this problem relevant to the center. You'll see why pretty soon. Like this works. It's just kind of like a fair amount of steps conceptually, but we can absolutely do it. So we've got 0.56 times 0.265. Getting what is that? 0.1484 kilogram meters. It's blue number. And then we can also combine these things on the other side of the equation. The 0.72 times the 0.325 is going to be 0.234 kilogram meters. And then we've got this just kind of coming down algebraically. Got the same thing there. We can isolate for x2 by bringing this over to the other side of the equation. So if we subtract 0.1484 from this other number, we should be left with, what is that? 0.0856 kilogram meters. And then we've got our number here. So we divide that by 0.6 or 0.16. And we'll get an answer of 0.535 meters. Now we can double check to see if that makes sense or not. And it does seem to make sense to me. I'm just kind of thinking through this problem. They were asking like how far this apple is from the other side. So if we're saying 0.535, that seems pretty reasonable to me because it's gone past the center of mass, and it seems to be pretty far past. So I can see that it's most of the way to the end here. So that kind of makes sense to me conceptually with our thing that we're talking about with like the small child, like putting the apple further out to the side, as well as like the usefulness of the visual diagram. So that is just one point of view. We're going to do the exact same problem, but we're going to look at it from these other 2 points of view and compare. I think it really helps you understand how this formula works to do that. Feel free to skip ahead if you're like, okay, I think I'm kind of getting how this works. So we also need to talk about sig figs. The rest of the video, I don't really do the correct sig figs. I've got numbers just doing the math so that they come out to be the exact same number no matter your reference point, but some of these reference points, they're going to throw off your sig figs because they have some uncertainty themselves. So if we move 1 meter to the left, is that exactly 1 meter? Is it 1 meter 0.00000? Like, that's going to affect things. But in this case here, we have, I believe it's 2 sig figs being multiplied, and so these get limited down to 2 sig figs. And ultimately, this ends up being 0.54 if you were to think about this using sig figs. But for most of the problems, I'll just be getting like the raw number without rounding, just to prove that the math works out to the same point. So from this reference point, I'm going to reuse a fair amount of the diagram just to save us some time, but you're going to want to do the same thing that we did last time where you're like trying to think through what makes sense in terms of the numbers here. And now our reference point is not on the side, it's in the center here. So we're going to change this and move it over to the side there. Our got it in green here. So we got our reference point right in the center now. and we are actually using the displacement that they gave us. So that is appropriate to use here. So I'm going to use that as my x1 value now. So that's nice because we have a number to just kind of plug in here, and it's going to be relevant to the center, making it just a little bit faster in terms of plugging in these parts. So we have m1, we have x1, we have m2. We do not have the displacement of x2, but we do have m total indirectly. Once again, we can get that from these other two masses. And this displacement is now, for the x center, it's 0 because we're at the center of mass. So you're 0 meters away from the center of mass, and your reference point is the center of mass. We're just going to say that that is 0 on our diagram. And this is where what I was talking about with the formulas is we're seeing a couple things cancel out. One thing might be in a positive direction, one thing might be in a negative direction, but that kind of depends on your reference frame. So I'm looking at this, I'm thinking I'm going to do this as my positives and this is my negatives, just to go with our normal convention of left and right. But this is where the in the intro of the video, they did like this stuff is equal to that stuff. They basically are saying that you have this positive piece is equal to some negative piece in terms of their magnitudes, which is totally correct. It's just, it's better if you can think through this in terms of stuff with directions and actually doing the center of mass on there. So we have a similar example here, but we don't have two masses in one direction, we just have one. We'll be doing that in the next problem though. So we just kind of plug in what we've got. Obviously anything times 0 will be 0, so it makes the math just a little bit faster here. So if we decide that this is going to be a positive value here, then that's fine to just kind of leave as is. But I am going to make sure that this is a negative displacement. So that kind of multiplies out as a negative number. So if we do, what is that? 0.06 times 0.56, 0.0336 kilogram meters. That's our number for our cereal box, how much that's contributing. And that should cancel out. So we can actually just bring it over to the other side. So if we added that to both sides, we'd get this, and then you divide by the 0.16, and we get an answer of 0.21. So our distance that x2 is away from the reference point is going to be 0.21 meters. But remember, this is only long, I think it's like about 3.5 or 3.25 for this whole side. So this is about 2/3 of the way down. So how I drew this was actually pretty good in terms of the scale. This is pretty close. I might want to actually show that a little bit closer just to make it actually closer to scale. But that's how this works. And it's really tricky when professors like take this equation and just kind of rearrange it and then don't tell you how it's been rearranged. But that is a pretty common thing in the college classes, so just be aware. So similar to before, we've changed the reference point here, so all of our distances are going to be different, but we still have the same masses, and the objects are still in the same places relative to each other. We're just looking at it from a different perspective. So we had previously stated that this distance from here to there, I think was 0.3 something. What was it? 0.325, but we used 0.265 for there. So we've got 0.265 for this distance from here to there. But then we have an additional distance of 1 meter from here to there. So if you want to show really the new displacement for the cereal box, this x1, that is going to be the 1 meter plus the 0.265. So we don't want to use that number that we had previously been given. What we really want to be using is this as our displacement value. And yeah, you can kind of see that in this diagram where it's like, okay, this is actually a fairly large positive number to get to there. And we can do the same sort of idea with the center of mass. So the center of mass, we had said previously that the distance from the side of the cart to there was 0.325 meters, but now we really are going from here to there, so that's 1 more meter. So 1.325 meters for that displacement. And it's the same sort of idea. We have all of our values. You can just kind of plug them in and solve. But it's important to make sure that you've actually plugged in displacements that are relevant to this problem. It's pretty easy to use the wrong displacement value, especially with like looking at those previous problems and then going to this. So we want to be just a little bit careful there, but it should be fine. So let's go ahead and see that. We've got 0.56 times the 1.265. Okay, we've got 7084 kilogram meters, and then this other side we've got the 0.72 times the 1.325, okay, 0.94 kilogram meters, and then we can bring that over. I believe, let's see, minus 0.7084. Okay, so we're getting 0.2456 for that number, and then we divide by the 0.16. And we're getting displacement of, oh, hold on, that's an error. That shouldn't be multiplied. 0.2456 divided by 0.16. Okay, so now we're getting 1.535 meters for our displacement for x2, which seems pretty good to me. I think that, you know, it was 1.535 meters. Yeah, it's like definitely past one meter. It's definitely past the halfway point. And so, like, if you remember before, we were, I think, getting 0.535. Yeah, and so we're just 1 more meter over. So you can see how this is useful to see this compared to that first one. You will get the same point in space, but it'll be relative to your new reference point. So you just have to be very careful about using the correct x values in these problems. So similar to the last problem, we have a shopping cart that is trying to be balanced, and we've now got 3 objects in the shopping cart. But the shopping cart is still 0.65 meters, and we still have the same center of mass right in the middle. And now we have, let's see, we've got a box of cereal, and they're telling us that the box of cereal weighs 0.56 kilograms, and they're giving us the displacement relative to the center here as 0.10 meters, possibly for x1 if we're talking about relative to the center. And then we're having the apple cider here. So there's some sort of apple cider here being placed directly on the center. And then we've got some apple that's being placed somewhere over here. So those of you who are kind of quick, you're going to notice that this center object is on the center of mass. So it doesn't really throw off your center of mass by having more mass. There are some slight differences. I was just looking, the distance is a little bit further out here, so the apple will have to be a little bit further out, but we can use the previous problem to just kind of guide ourselves and see, like, was our answer actually reasonable or not. So same sort of formula. We're just gonna kind of set this up, same deal as we did before. We've got our m1 x1 plus m2 x2, and we actually have 3 objects now. And then we've got our mass total times the center of mass. And we are doing this relevant to the reference point being over here. So we need distances that are relevant to that. So if we do 0.65, then we can say that our center of mass is going to be that 0.325 meters, like we saw in the previous problem. You get that by dividing the total distance here in 2. And so we have that number. That's one of our givens. We do also have the m1. That's just directly given. We do not have the displacement being directly given, but it is something that we can solve for. So this is not what we want to use for our x1. What we want for our x1 is actually going to be relevant to here to there, because this is relevant to the center. We're trying to do relevant to the left side right now, or relative to the left side. So x1, what we actually want to use for that is going to be over here. So it's going to be the 0.325 minus 0.10, so 0.225. So that's something that wasn't directly given, but something that we can easily solve for. We have the mass 2 that was given for the apple cider as 1.9 kilograms. So we've got that just being given directly, and the center of mass was something that we were able to solve for as well. Then M3, we have the mass, and we're going to end up solving for x3. That's going to be our missing piece. M total has, similar to the last problem, not been directly given, but it's pretty easy to calculate. You just add up your different masses. So if we look at those different masses, we've got the 0.56 kilograms plus the 0.16 kilograms plus the 1.9 kilograms, and we can find our total mass. So if we do that, let's see what we got. 0.56 plus 0.16 plus 1.9. Okay, so our total mass is going to be a 2.62. So if we look at that, then we can start plugging in some of these numbers. M1 was at 0.56 kilograms, and it was times that displacement of the 0.225. And this is where the colors they're just invaluable. They're just super, super valuable. So we've got our M2 and our displacement 2. But the interesting thing is that the displacement 2 is the displacement of the center of mass. So this is actually going to be that same number, that 0.325 meters. And we've got M2, which was the 1.9 kilograms. And yeah, you don't want to multiply the wrong one by the wrong one here, right? So you got to make sure that you've double checked that you've put the right mass with the right distance. And then we've got our mass and our displacement for the apple. So the mass is 1.16 kilograms. And then we're going to look for x3 right here. This is going to be what we're ultimately solving for. We have M2, 2.62 kilograms, times that by our displacement, center of mass, and this is where you want to be careful with all of your math. It'll take us a bit of time to do it, but we should be able to do it. 225. So we've got 1.26 kilogram meters. Just keep that blue for my brain. And we've got our second number there for our apple cider, or not apple cider, apple vinegar, I think. Yeah, I think it was a vinegar. Yeah. So if we do that, then we should get something like this in kilogram meters. So we should be looking pretty good with that. And then we just need to get this last piece on the other side of the equation with our center of mass. And then we should be able to relate these different parts. So we get 0.851. Okay, kilogram meters. And we'll just drop this down. And we will need to bring this over to the other side. You might want to combine them beforehand, or you can just kind of do it all at once. But we should be able to get something. Okay, this is where you want to be able to do your concept checks, because I was getting numbers that just didn't make sense, and it's because of a small calculator mistake. So you gotta be just really on double checking your answer at the end to see if it makes sense here. That's really the best way to double check this. But with that correctly done, then we can also see that in this problem, our reference point is going to be on the left, meaning all these numbers are positive that we're working with for displacements. So all these things should be positive. I was getting like a negative value, which means the apple would be over here, which would make no sense. So if we actually use this correct value here, we can get 0.6175. Okay, 0.7435 kilogram meters being equal on this side plus that displacement and mass to the center of mass. So we just do a little rearranging. 0.8518 minus the 0.7435. So we've got that number now on the left, 0.108 kilogram meters being equal to this, and we can just divide by the 0.16 kilograms to get that displacement. Okay. Interestingly enough, it appears that X3 is going to be not in the cart. So we can't actually balance this problem as is. We would need to bring that cereal box closer in, but we are getting a value here of, sorry, I was just double checking from the other reference point. We got 1.08 divided by the 0.16. So we get 6.75 meters, which means this apple is actually outside of the shopping cart. It's kind of like out here a little bit. But that's okay. You know, for our purposes of this problem, we can see how this now is not in the cart. And that's actually going to be a concept question that a lot of professors are going to ask you. So you're going to need to be able to identify where an answer makes sense or not in a problem like this. So it's a little bit weird, this one, being outside of the cart, but we can look at how these other values are kind of making this be positive, but not quite positive enough. And then this needs to bring up that positive number enough to make the average go right here. Because if this wasn't far out enough, the average wouldn't be here, it'd be kind of further to the left. So yeah, it's kind of tricky the math on this one, but it's doable. There's a small error in this diagram. This should be going to all the way to the left side. We're starting with our reference point being originally from that left side, so this diagram should be showing that. So this is showing that this is a little bit further than the cart, which was 0.65. So this is going a little bit past the cart from that left side point of view. So if we look at the reference point in the center, the math is actually really, really easy because two of these things, the displacement is just 0. So the x center of mass is still the same as x2, but in both cases it's 0 because our reference point is there. So now we have a matter where something is negative in terms of its overall value. This thing's value is going to be 0. And now this thing's value will be positive, and they should end up canceling out appropriately. So it's just a matter of trying to figure out what displacement you're going to use for x1 in here to end up getting a center of mass of 0, so that that whole part ends up calculating out to 0. So we've got our m1. And its displacement from the center, I believe, was given in the problem. So they just told you it was 0.10 meters here. So 0.10 meters is directly given. So we know that for sure. And that's going to be multiplied by its mass. And then you could plug in these numbers, but because this displacement is 0, you're going to end up multiplying out to 0 anyways. And then we've got this mass here, which was the 0.16 kilograms times its displacement, which is what we're solving for, equal to 0. Knowing that this calculation is also going to end up having a displacement of 0. So if you multiply any number by 0, it ends up being 0. So if we just multiply our 0.56 times the 0.10, we get 0.056 kilogram meters for that. That's contributing to the center of mass, and that's going to be added to this, which is equal to 0. We can see that the displacement value here actually, if we're thinking about this, I'd said this should be negative because its displacement was negative, and that will then give us a positive x3 value. So if we're doing left being negative, right being positive, that should work. So you can rearrange, bring this over to the other side of the equation. That's being equal to this now, and you just divide by that 0.16, and we should get a number. Okay, so x3 in this reference frame is 0.35 meters away. But that does seem to match what we got in the previous problem, because you're saying that this distance is more than half the cart. Because remember, half the cart we had said was 0.325. So this is 0.25 past that. So it does seem to match our previous calculation on this problem. So similar to the last time, we're going to have this be off to the side, but now it's not 1 meter. This is going to be 1,000 meters. We could do 1,000,000 meters or however big of a number that you want, but this is, we're going to just kind of prove that it doesn't matter how far off you go from the side here, you still get the same point in space. It's just relevant to a different reference point. So we'll have this reference point over here, and we'll have relevant displacements. So we can use some numbers that we previously had calculated. We had said that this to there was 0.325. So now going from here to there, you're going to get 1,000 meters, 0.325. So it's pretty far to get to the center of mass. But that's going to be your x2 value as well as your x of the center of mass. So we have that one value. we had previously said that this was 0.225 meters from here to there. So if we really want our displacement, we're going to need to go from here to our reference point, which is going to be 1,000 meters, or 1,000.225 meters. So we have x1, we have x2, we have the displacement, and we have all the other masses. So it is a little bit weird to do it with such a big number here, but it should work out. So we've got our 1,000.225 meters times our mass of 0.56 kilograms, and then that's going to be multiplied or added to this mass times its displacement. And I believe that that mass was, the 1.9 kilograms. And then we're going to have our last mass with the unknown displacement. This is M3, which we had said wasn't it? Yeah, 0.16 kilograms. And then that is equal to, it's the same total mass as what we had previously, so 2.62 kilograms times the displacement of the center of mass, which is the same number that we've got right here. So yeah, just be careful with your math here, but it should be doable. I might make a small mistake. It's tricky numbers. Got weird numbers. Okay, so do that. 560.26 kilogram meters. Our first number, gotta keep that in blue. Then 1.9 kilograms times that 1,000.25. 900. Yeah, these numbers are getting a little bit big. Meters, and we'll keep that in gray. And we've got this unknown times the 0.16 kilograms, which is now equal to 2.62 times 1,000.325. So what's that? 2,620.8515 kilogram meters. We've got definitely some big numbers here, but you can see, just like concept check wise, that you've got two positive numbers. They're helping, but we need another positive number to kind of bring us up to that. So it does seem to match our reference frame. So if we can add the 560.126 plus the 1,900.6175. Okay. 60 point, what was it? 4 kilogram meters. And just copy that all over. I really like doing this just a little bit slower because you can then double check your math where it's likely to be a little bit off here. So we've got the 2,620.8515 minus the 2,460.74. So I'm getting 160 point, what is that? 115 kilogram meters, which is equal to this. We should be able to then solve for x3. So it's a little bit off, but that's because of the sig fig issue. I think I may have cut off some numbers here, and so it's a little bit weird, but we're getting something that's close to what you would expect, considering that sig figs, when you're doing 1,000 here, it's kind of throwing off your accuracy on the like tenths of a meter, just because it's, yeah, there's a lot of sig figs in those said numbers. So getting something that's a little bit more than 1,000 here, 0.69 meters, seems to match what we were getting previously. It should have been more like 0.67 if we had kept those other sig figs on there, and you can double check that if you'd like. I'm curious, you could put a comment down for the exact number that you get, but it should be close. So this problem is similar to the example problem shown at the beginning. With 3 objects, we're trying to balance them and figure out where they go to get the center mass to be right in the center here. So if we think about, in this problem, I made the shopping cart a bit wider. The cereal is going to be placed almost all the way to the left, but not all the way. The apple cider will be placed to the right a bit. And the apple, I think it's going to be somewhere over here, but it's hard to say right now. But it definitely seems like we've got a pretty heavy object kind of far out. And then closer, you've got a heavier object, but it's pretty close. So I believe that because this is so close that the apple will need to be on this side to kind of balance things out. But this would be hard to know just intuitively. Like a little kid looking at this would not necessarily be able to do it intuitively just by looking at it, but by playing around with it, they'd probably be able to figure out where this apple needs to go to balance these two out if you have them placed. So let's go ahead and start plugging in and labeling stuff that we have, information that we have. So they've given us our relevant masses. Kilograms, and then this is the 0.16 kilograms. And now the shopping cart is a little bit of a different width, 1.3 meters. And we're having this first problem start where we're looking at this from the left side of the shopping cart. So if we had said that here to there from the center is 0.60 meters, then that means that our displacement is going to be half of 1.3 minus the 0.60. So we can see that the x center of mass is just half of that. So let's get that number. 0.3 divided by 2, 0.65 meters. And then if you look here, if this is a length of 60, then this should be a length of 0.05 meters. So we do have x1 and m1. So we've got m1, x1 plus m2, x2 plus m3, x3 is all equal to the total mass times the average position, or the center of mass. So we have mass given. This was pretty easy for us to solve. Let's see, we do have this given, but the displacement of the apple cider is going to be relevant to the distance that they gave here. So they gave us 0.12 meters. That's going to be added to the 0.65. So the total distance here for the x2 relative to this side is going to be 0.65 plus 0.12 is what I'm seeing. So we get 0.77. So we've got that number as well indirectly, but it is solvable or knowable. We have this, and we're ultimately solving for this unknown displacement piece for this apple. We again have this total. It's the same, I believe, from the previous problem because we've got the same objects. And we have a displacement of the center of mass which is known. So that's something that we just have. So we just kind of plug things in, and you can see algebraically we have everything besides x3, so we should be able to solve for this. So let's go ahead and do that. So we got our 0.56 kilograms for M1, I believe, the cereal box, times its displacement, 0.05 meters. Yep, that does look like that's the correct number for mass with that displacement. I'd say it's worth double checking on these longer problems, each variable, honestly. M2 was at 1.9 kilograms, and the displacement for that was this x2 number, 0.77 meters, plus M3, which is 0.16 kilograms, times whatever value that we're going to get for this, which is now equal to the total mass times that displacement. And our total mass, we did previously calculate it, but it's just these numbers added up. So we get 2.62 for that total kilograms there. And the center of mass displacement is half of this cart's length, so the 0.65 meters. So I'm just double checking that I've got things relative to this left point, because that's a pretty easy mistake to accidentally look and get a value from a different reference point here. But it looks like we're going from the left side here, and it does seem to match that in my calculations. So we just kind of plug in and see what we get. Double checking it, of course, with some reasoning. And a lot of my students try and rush through the math on this part, and this is where like most of my tutoring I end up working with students is like, hey, just slow it down here, write it out, make it so that you can double check it. So we get that. And then whatever value you get from this calculated piece. All of these should add up to our sum of our masses at the average location. 6.5. Okay, so I got 1.703 kilogram meters. And I'm just kind of thinking about these. Yeah, all of these are positive values. Like this is a positive value, this is a positive value, this is a positive value, and this is a positive value in terms of these reference distances all should have positive magnitudes. So then we get to, we're almost at the end of this one calculation. We just got to combine a few of these pieces. So 1.463 plus the 0.028. Okay. 491 kilogram meters. And we'll combine those two. Yeah, and it does seem that x3 should end up being positive from the values that I'm getting here. So we've got 1.703 minus the 1.491. Okay. I'm getting a value of 0.212 kilogram meters is equal to our displacement times our mass there. So in the end, we end up getting an x3 value of 1.325. Which does seem to make sense to me. It's just a little bit actually outside of our cart. So this again can't go in the cart with how we've built this problem. So you got to think about this. A lot of like ChatGPT AIs, they'll give you a number, but they might miss like what this actually means in the context of the problem. But if we're looking at this displacement, which I'm going to do in orange, it does seem pretty reasonable to have that be the 1.325, seeing how this is 1.3, and it's like, yeah, it looks like this is not quite enough to balance that being that far out. So we needed to have something far out on this side as well to balance it. Okay. So when we use the reference point as being the center of mass here, this problem is a bit easier in some ways because they gave us the numbers relative here, but it's very, very similar. One important caveat is now that this value, the center of mass, that's going to end up being 0 when you do this. When you have your reference point being at your center of mass, the distance is 0, right? So you've got that as your reference point value, and that's going to be pretty straightforward. Now there are going to be, it looks like in this case now, things where like this is overall on the left side, and these are overall on the right side, and so we're just kind of balancing those out. We do know from the previous problem that this thing has to be on the right side, but you would be able to see that from the values at this point. If you were to kind of plug in these two, you'd see like, oh yeah, this has to be a positive value over here. Otherwise, the math doesn't work. So if we do 0.56 kilograms, that is going to be times the x1 displacement, which I believe the problem gave as 0.6 meters. Yep. And we have M2, which they gave us, I think it was like 1 point something. It's like 1.2 or 0.12. Yeah, 0.12 meters there. So we've got that x2. And we've got our mass, 9 kilograms. And then this mystery number times the third mass. So we've got the 0.16 kilograms times x3. Now all of this adds up to 0 right here, meaning that things need to cancel out to some degree. So this, remember, we said was going to be a negative number because we have a negative displacement here. And so you can get this as a negative number and see that how it compares to this positive number. 6 times 0.60. We got a negative 0.336 kilogram meters from those two being combined. And then we've got our 1.9 times 0.12. Yeah. So you can see right now that the positives are kind of losing to the negatives. Like the negatives are bigger, so you would have a negative center of mass currently. So we need to have this be a positive value to bring that center of mass to the center of this cart. In other words, this problem would not be able to be equal to 0 as an expression unless x3 is a positive value. So we just combine. That's a negative number plus the 0.228. So that's a negative 1.08, but we can, bring that over to the other side of the equation. So we've got negative 108 kilogram meters. Just double checking the units are the same thing. Yep, it does look correct. So technically, this is all equal to 0, and then you can rewrite it as this being equal to the 108 kilogram meters, and we should be able to solve for this number now. Yeah, So I'm getting x3, a value of 0.675 meters. Which is, yeah, seeming pretty reasonable to me in this context of this problem right now. So if we look at the diagram, going from the center to here, having 0.675 does seem pretty reasonable because we had said going from the center to the side would be 0.65. So it's can't solve in carts. Like this needs to be going off the cart. So realistically, you're gonna need to bring in that cereal a little bit to get this apple somewhere in the cart. So if we're doing something that's really far away, this is gonna cause some sig fig issues, but it's due like a million meters away from the cart. We can still do this math and it still does work out technically. It's just like realistically due to sig figs, it's gonna be hard to actually get accurate numbers. But if you have something like this big, and we know where all these things were relative to the left side, we just add that to 1 million. So this is no longer just 0.05, this is 1 million 0.05. So it's going to end up causing our numbers to be quite a bit bigger. But it is all doable. So it's, yeah, kind of a pain to actually type it all out. But it can definitely be done. So this is now 1 million 0.077. I think you're probably getting the idea here. And it's just a matter of just kind of plugging in the numbers and seeing how it works. So we'll go through how that works. So we've got 1 million 0.65 because now like this is all relevant to that much further away from than when we were at the left side. So we're gonna have some pretty large numbers now for our values, but we should be able to end up solving for our x3. Okay, so if we take this 0.56, we're gonna times that by the 1 million 0.05, 500,000. That was 560,000. 0.02. Eight kilogram meters. And then we've got our 1.9 times the 1 million 0.77. 1,900,000 001.463, and then we've got our 2.62 times the 1 million 0.65. Yeah, it's some big numbers. And realistically, the sig figs on this is just, it's not going to work out very nicely. So we're kind of going outside of reality and measurements and accuracy, just to make this math doable. As you can see, these are big numbers to combine. So if I've got that number right there, plus this guy right here. Okay, I think I'm gonna have to enter it in. 0.3. That 460.491. So we then can bring that over to the other side of the equation. We'll do a little subtraction. 2,620.001.703 minus 2460001.491. Oh, sig figs. Yeah. See, this is what I was saying is you gotta just be kind of careful with these numbers. Okay, that's actually the correct number that I was supposed to get. So 3 minus the 2,460,000. Okay, there we go. So that's our, what is it? 160,000. Point 212. We divide that by our 0.16, and we're getting 1,000,000 plus 1.325. So this does work out the same. We're getting the same value. Three, 2, 5. It's just like, why would you do this from this far away? But it holds. The math is equally valid from this reference point as any other reference point. So yeah. So this is a bonus question. We have our shopping cart, which we are assuming to have no mass. Obviously it should, but we are going to just be considering that its mass kind of averages out, and we're just really going to consider the cereal box and the apple. Now, in this case, we don't know where the center is. We don't have the center of mass, but we have some other values here. So there, you could have your reference point be in the center here, which is kind of what I'm thinking because they've given values relative to that. But that doesn't mean that's where the center of mass is. So we're going to have like, it looks like some sort of x1 value, some sort of x2 value, and I'm just thinking that the center of mass is going to be closer to the heavier thing probably. So I'm betting the center of mass is like somewhere. So this is our reference point. Now our center of mass is like somewhere like here. So this is now going to be like XCM. So we've got some sort of displacement now relative to the center of the cart. We could have easily picked the left side of the cart or 1,000,000 meters away. All those are equally valid. This just is matching the numbers that they've given us. So we have M1 x1 plus M2 x2 is equal to the M total times the center mass's position. And we have a lot of this information. We have that mass, we have that position, we have this position, and we have, actually, you know what? I'm just, to keep colors consistent with the previous section, let's do that as the position. And this is our mass. This is something that we can solve for pretty easily. And then we are ultimately going to be trying to get the center mass position. So the total mass here is just the two added up. So I think that that was 0.56 plus 0.16. Say it with me. 0.72 kilograms. So we've got that times this mystery number that we're not really sure what that displacement is. And that's going to be equal now to this M1, X1, M2, X2 thing that we have. It is important to note, though, that there is some direction to these things. So in this context, we had said this was going to the left, this is going to the right. So these things will have positive and negative values that aren't going to perfectly cancel out because we're not at the center of the cart anymore. So this displacement should, I think, end up being negative because the negative's a bigger value. So we got our 0.56 kilograms, and its displacement of negative 0.10 meters plus a mass of 0.16 kilograms times a displacement of a positive 0.30 meters. And that should be equal to all of this. And we just kind of plug in. We have everything here besides this, so algebraically this should be solvable. So 0.56 times 0.1 is 0.056 kilogram meters. That. And then we're going to have our 0.16 times 0.30, 0.048 kilogram meters. You may be like, wait, what? Hold on. This needs to be negative. Yeah. You got to make sure that you're checking the diagram to know which of these parts will be negative and which will be positive. If you look above, this was going to the left, so it should be fine. And then we can combine those two terms, and we should be able to get this pretty soon. We've got that. It's 0.056. I'm getting a negative number right here, but that's okay because the center of mass was most likely going to the left, which matches what we kind of stated there. And let's see, 0.008 divided by 0.72. Yeah, so this x center of mass is a negative number. It's slightly to the left, and it's not a tenth of a meter, but like a hundredth of a meter. If we're doing this to like 2 sig figs, actually, this would be like 0.11. And that would be how you'd go through a problem like that. It's very similar. You're just trying to figure out what you know and pick a reference frame that makes sense to you or with the problem that was given. But this, we could do the two other ways if we wanted to with different reference points. This just was easy with what they gave. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there. And we can schedule hourly appointments. I've got a few other things on here like a Facebook page and our social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.